All right, so today we're going to be doing some practice with our new chi-square test for goodness of fit. We're going to do this using a Desmos activity. So I'll drop that link into the chat so y'all can click on that and join the activity. You will be restricted to the very first frame of that, which will be a check-in screen. So that link should be coming through right now. Or if you prefer, you can always go to student.desmos.com, go to our class, and find the 11.1 chi-square test for goodness of fit activity. Cool. So kind of as we've done in some of our previous Desmos activities, the first few slides here will be a review of what we saw yesterday. Obviously not with as much time spent on it, but just a quick little review of the key things that we're going to need and that we're going to use. All right. So I'll just be adding the screens as we go. You should now be able to go to the next screen, which looks like this. All right, section 11.1 is on the chi-square test for goodness of fit. Right? The chi-square test for goodness of fit allows us to test a claim about a distribution of categorical data. This is different than the previous inference methods we have used because it allows for testing the evidence for or against an entire distribution rather than just one value within the distribution. So rather than testing each value in a categorical distribution against an alternative, which would be very time-consuming, we can test the whole distribution with the chi-square test for goodness of fit. And that's what we're going to work on today. So this is how we calculate our chi-square test statistic. Right? This is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared equals the sum of the observed minus expected squared divided by expected, right? Where the sum is over all possible values for the categorical variable. Right? This is similar to, I guess it would be most similar to the variance. I kind of related to standard deviation yesterday, but it's more closely related to variance. It's telling us how far away each thing is from what we expect. All right, so that is our chi-square statistic. We use that chi-square statistic on our chi-square distributions, which is our third type of distribution that we're using in this class. We have our standard normal distribution. We have our T distribution that we use from that's table B, right? And now we have table C, which is our chi-square distributions. I know that this type came out really, really small on that left-hand side. I apologize for that. But it does say the chi-square distributions are a family of density curves that take only non-negative values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square test for goodness of fit uses the chi-square distribution with the degrees of freedom equaling to the number of categories minus 1. So a major difference between this degree of freedom and the degree of freedom we use when we're doing sample means and significance test confidence intervals for that is that this does not depend on the sample size. It only depends on the number of categories. Right. Then we have some things to keep in mind about our chi-square distribution. As the degrees of freedom increase, the density curves become less skewed and larger values become more probable. The mean for a particular chi-square distribution is equal to its degree of freedom. And for degrees of freedom greater than 2, the mode or the peak of the chi-square density curve is at degrees of freedom minus 2. And this makes sense, right? Because the direction of the skew pulls the mean, right, towards the skew, so to say. So if we go to the left of the mean that's closer to the peak. We also have our conditions for performing a chi-square test for goodness of fit. All right. We have the random and 10% condition, which are the same random and 10% condition we've used for all of our previous tests. Right. The large counts condition is different than the large counts condition that we check with proportions. All right. With proportions, we have to make sure the number of successes and failures are both at least 10. With our goodness of fit test, the condition is that all expected counts are at least 5. I have to have at least 5 things, whatever those, color, whatever, in each of those categories. Okay, so that is the major difference. We have all the parts so that we can now do a chi-square test for goodness of fit. Though it is not stated specifically here, when you're doing a chi-square test for goodness of fit, you need to do the 4-step process. State, plan, do, conclude. Right? If you don't really want to write state and then a thing, plan, and a thing, you need to at least have all those parts. You don't need to specifically label it, but you should have a statement saying what you're going to do and the test you're going to use, a checking of the conditions, right? A statement saying what inference method you will use, and then doing that inference method, the calculations, and then a specific conclusion statement, tying it all together back to the context. That's what the state, plan, do, conclude. It helps you organize those thought processes and then present them in a way that the graders want to see them. All right, that's why we're stressing it. All right, so when we do our test, if the conditions are met, right, we can determine whether a categorical variable has a specified distribution in the population of interest expressed as the proportion of individuals falling into each possible category, and perform a test of the null hypothesis, which is the stated distribution of the categorical variable in the population of interest is correct, or the alternative, which is that the stated distribution of the categorical variable in the population of interest is not correct. Right? And kind of a method to writing these is write your null hypothesis, which is the claim that blah, 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 blah is the distribution is correct. Then copy the entirety of that thing and then say is not correct at the end for the alternative. All right. We don't need to it's not like the null and alternative with other tests that we've done. We don't need to define parameters and things like that unless we really want to do it that way, which in my opinion, just opens yourself up for more things to be graded, right? So there's that, right? We're going to start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic. Chi-squared equals the sum of the observed minus expected squared divided by expected, where the sum is over the k different categories. The p-value is the area to the right of chi-squared under the density curve of the chi-square distribution with k minus 1 degrees of freedom. All right. And so this is chi-square test for goodness of fit in a nutshell. We're following a lot of the same processes that we've done already with our other tests. We're now just looking at a different context and a different set of things. So now we will practice with some of these things. So first, we're going to compute some expected counts. We have our context here. Jenny made a 6-sided die in ceramics class and rolled it 60 times to test if each side was equally likely to show up on top. Assuming that her die is fair, calculate the expected counts for each possible outcome. All right, so you'll just fill in the middle of this table here. If your value is incorrect, it will tell you it is incorrect. If it is correct, you'll get a green check mark. All right, so this will give you immediate feedback on whether or not you're doing stuff correctly. All right, so we'll take a couple minutes here to answer this question. So many of you who tried this problem, looks like you were able to get it to the correct place. Now, I want to point out in this context, we weren't given specific proportions for the likelihood of each side of the die occurring, but we're given a hint. Right? What in the context tells us what's the probability of each side popping up? Sometimes it won't be specifically stated, but it will be inferred, and you're going to have to figure that out. $60 times. Okay, so we're all saying in the chat 60 times. What do you mean by 60 times? So I know we rolled the dice 60 times. There we go. Right, so we rolled the dice 60 times, and then Brian has in here that it's equally likely. Yes, that's what we're looking for. We have two statements in here that kind of give us this. We have equally likely, right? That's essentially our null hypothesis, is that each side is equally likely to occur. Meaning if we have 6 sides, we have a 1 in 6 chance of any of those 6 sides happening. We also have assuming that her die is fair. Again, implying that each of the sides is equally likely, because that would imply a fair dice. Okay, so even though it's not said, we can imply this information from the context that each side has a 1 in 6 chance of occurring. Right, which also means that we just evenly distribute the 60 rolls of the dice between all of the sides, and we get 10s for each spot. All right, and so this happens when we have an assumption of an even distribution, or everything is equally likely, or it's fair. Is there anything I can clarify about this example? So we'll do another expected counts question here, but now we have things that are not equally likely. As we have a company that claims that each batch of its deluxe mixed nuts contain 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts. To test this claim, a quality control inspector takes a random sample of 150 nuts from the latest batch. Calculate the expected counts for each type of nut. Again, fill in the middle of the table. It will tell you if you're correct or not. Okay, we'll take a few minutes on this one, and then we will talk about it. Okay, so now on this one, I see a lot of good work going on into this table. One thing I do want to point out is when we're calculating expected counts, it's okay to have a decimal. You do not need a whole number for expected counts. Typically, when you're looking at observed counts, you're going to have whole numbers. That just kind of makes sense for what, how experiments work. But for expected, because we're averaging out stuff, you're going to get decimals sometimes, and that's okay. All right. So I see a lot of correct answers. Let's see what this is. So now when we're calculating our expected count for each category, all we're doing is taking the sample size and multiplying it by the percent probability of that nut, at least the assumed proportion. So you get 150 times 0.52, 150 times 0.27, 150 times 0.13, 150 times 0.08. Please make sure when you convert your percentage to a decimal that your decimal is in the right place. All right. So that ultimately gets us 78, 40.5, 19.5, and 12. All right, so if their claim is correct, we would expect on average to have about this distribution of nuts in a set of 150. Right. Is there anything I can clarify about this example? So we've seen one where we have stuff that's equally likely, one expected counts calculation where they are not equally likely. So we have our expected counts. We're keeping with the same context. We will use this context basically for the rest of this activity. Now we want to state appropriate hypotheses for performing a test of the company's claim. We need a null and alternative hypothesis. Again, I do recommend writing 2 statements for this. Don't try to define each of the parameters. Write the statement. Basically, the null is that the claim is true. The alternative is that the claim is not true or is not correct. You got to fill in the details though. All right, so I'll give you all a few minutes on this one and then we will talk about it. All right, let's talk about this. So there's a couple of you that it looks like you have a good idea of how to do this. Some of you guys are still kind of struggling to put the ideas together. If you're using parameters, which means you're saying like the null hypothesis is that P sub something is this, P sub something else is this, and this is that. Once you've labeled all that, you have to tell everyone what that is, what each P sub whatever represents. Right? So there are extra steps in writing your hypothesis that way. So please understand that. All right. Alternatively, right, if we write our null hypothesis, do this real quick. Is, well, I can type, I promise. Right, that's the easiest way to write your null hypothesis. Take what it's saying is true. Right, the company says this is what it is. Throw that in your hypothesis. Right, so the company's, well, that's not the right company. Sorry, English is not my major. That's proper, I believe. Companies claim that each batch of its deluxe mix nuts contain 50% cashews, blah, 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 is correct. Right? Or you could say some derivative thereof is true, you know, something like that. And then we will just repurpose this. And we have the alternative. Right? Don't work harder on writing these than is needed, right? Because the only difference when we're doing this kind of test is the distribution is correct or the distribution is not correct. We just have to give the proper details for our hypotheses. Right? Is there any questions? Anything I can clarify? Yeah. We're going to go to the next piece. So we've gotten our hypotheses. Right? We know our observed and expected counts. We need our chi-square statistic. All right, so we're going to use this table below. It's already populated with our observed versus expected counts for each category to calculate the chi-square statistic for the distribution. Right, we're going to need to use that formula that's on slide 3 of this presentation. Okay, that might be helpful. You're also probably going to want a calculator. So if you have your graphing calculator, please use that because you should be getting more used to using that. If you do not, you can use your phone, that's fine. Or you can use Desmos calculator as well. We'll give you all a few minutes here to do this calculation and then we will review it. Alrighty, so for this one, we need to use that chi-squared statistic calculation. So we're going to be adding basically how far away each observed versus expected count is for each of the 4 categories. So we're going to have 4 fractions that we're adding up in this. Right? We're going to have observed number of cashews minus the expected number of cashews squared divided by the expected number of cashews. Right? Observed number of almonds minus expected number of almonds squared divided by number of almonds, expected number of almonds. Right? And so on. We're going to do that for each one. Right. Ultimately, if we put this in our calculator, we should get the 6.5987 and so on and so on. Right. If you're getting a different value than that, that could be due to rounding. If you're calculating each fraction independently and then adding those results up and rounding each one of those things, your result might be different. The most accurate answer you can get will be trying to do all the calculation in one shot, as I've done here on the calculator. Right. If you do not know how to make a little fraction like this in your TI-84 calculator, you go to alpha, y equals, enter, and you get your little fraction to fill out. That can make it a lot easier to get things to calculate the way that you want them to in your calculator because you can make them look like you wrote them. Okay? So there's that. That can be helpful. All right. Now, a little bit more on rounding here. Most of the things we're going to use, like on our tables and things like that, only goes up to a certain number of decimal places, so we don't need to keep all the decimals, right? We're just not going to need them. We need to usually keep 2 or 3 decimal places. So rounding this to like 6.599 would be good. If you try to round any more, it's just going to go down, round down to 6.6, which for our needs here for this problem, that will be fine to have 6.6. It's going to land us in the right spot. All right, but if we were to round to 6.5, that's a really huge amount of rounding, and it's an improper rounding for this decimal. Right? Make sure you're rounding appropriately. The number to the right of the decimal place you're rounding to is above. If 5 or more, you round up. If it's less than 5, you round down. And rounding down means you don't increase the number. Right? All right, so this is what we should have gotten. All right, if you put 6.599 in here, it'll say you did good, right? If you kept more decimal places, it may not accept it because I have to like program in each different typed in answer, and I'm not going to put in like 70 different options because that takes a long time. So there's that. If you're close, that's good. Any questions on how we calculate this? Your calculator can do this all for you as well. We just haven't looked at how to do that on the calculator yet. There is a function where you put in all your stuff and it goes spit it out. All right, next. Same context for the next part. All right. We need to confirm that the expected counts are large enough to use a chi-square distribution to calculate the p-value. So, is the large counts condition met? Yes or no? It's pretty straightforward. You can hit submit to see if you selected the right option on that. Then, what degrees of freedom should you use? Please just type the number value for the degrees of freedom that you will use on table C. Let's take a couple minutes to answer these two questions. There's a submission button for both of them so that you can see if your answers are correct. Alrighty, so for the first one, large counts condition. Remember, the large counts condition is kind of the only new condition in this, and that is making sure that the expected counts for each of the categories is at least 5. If we look back at our table here, all of our expected counts are at least 5. We have 78, 40.5, 19.5, 12. Those are all bigger than 5. So our condition is met. Hooray. Now our degrees of freedom. Remember, our degrees of freedom is determined by the number of categories minus 1. I have 4 categories in this example, right? I have our almonds, our cashews, our macadamia nuts, and our Brazil nuts. 4 categories. So I have 3 degrees of freedom. If you did 150 minus 1, you use the sample size on accident. We do not use the sample size for degrees of freedom. We're doing a chi-square test. Okay, we use the number of categories. Next, we're going to use table C and find the p-value and make a conclusion about this context. Now that conditions have been met, we have the value of the test statistic, and we know the degrees of freedom. We're going to use table C to find the range of the p-value. Right? And to do that, we have a link here to our formulas and tables. Table C is the last table available in our formulas and tables list, the set. Right? It is the chi-squared table. So you're going to need to use that. And then based on that, you'll get a range for the p-value. This table C behaves very similarly to table B. We're going to get a range for the p-value and not an exact value. That's okay. The range will be enough for us to make a conclusion about the company's claim distribution for its deluxe mixed nuts. Remember that since a significance value has not been given, you should use alpha equaling 0.05. That is the default when 1 is not given to you. All right. So we'll give you a few minutes on here, and then we will talk about it. All right. Awesome. Let's talk about this one. So just like when we found p-values for means and doing significance tests about means, we're going to get a p-value between 2 numbers on this table C. Right, so let's look at table C. It's table A, table B, and table C. Right. Notice this top part here is the tail probability. That is our p-value. Those are the p-values we're trying to find. Right, we have our degrees of freedom here. We're not using, well, this many degrees of freedom, you'd have a massive amount of data. Still, all right, so we're looking here at 3. We're going to follow that row over till we're right here, right? Our critical value, right? Not the critical value, the chi-square statistic is 6.599, which is between 6.25 and 7.81. Then we follow that up, and we're between 0.1 and 0.05, sorry. Okay. Now when we're talking about values, we always want to refer to the lower value first. So the p-value is between 0.05 and 0.1. You can write it as an inequality to be a little more efficient. Where you can say 0.05 is less than p-value, which is less than 0.10. And click that guy, make it look prettier. All right. So this inequality describes where the p-value is. It's somewhere between 0.05 and 0.1. it is definitely greater than 0.05 and definitely less than 0.1. All right, this is enough to make a conclusion. Right, we could calculate with our calculator doing the work for us the exact p-value based on the information we have, but we don't have to. Using the table is enough. Right. So, what conclusion would we draw about the company's claim distribution for its deluxe mixed nuts? Well, using the alpha of 0.05, we know that our p-value is greater than that. When the p-value is greater than alpha, we fail to reject the null hypothesis. That means we do not have convincing evidence that the true distribution or the true proportion of each type of nut is different than what the company claims. Right. Essentially, we can't show that they're wrong. And it's important to word it in that we don't have evidence for something and not saying that they're correct, because they're not necessarily correct, they're just not incorrect. It's the weird way that statistics kind of works. Is there anything I can clarify on this part of the problem? So the last thing we're going to talk about here is the thing that was brought up yesterday, but it wasn't necessarily gone over in the PowerPoint, and that's our follow-up analysis. Essentially, the follow-up happens if you find significant results. And then you go back into your data and try to say, okay, well, what caused this result? What was the main contributing thing? All right, so when sample data lead to a statistically significant result, which is not what happened in the example we just saw because we didn't find evidence of anything different. Right, we can conclude that our variable has a distribution different from the one stated. When this happens, start by examining which categories of the variable show large deviations between the observed and expected counts. Then look at the individual terms, observed minus expected squared divided by expected, that are added together to produce the test statistic chi-squared. These components show which terms contribute most to the chi-square statistic. Determining which component contributed the most to the chi-square statistic will allow us to get an idea of which categories have incorrect hypothesized values. Right? Essentially, it gives us an idea of where the assumed value is wrong. But it could also give me another thing to test later if I wanted to continue more research on something, is to like, okay, well, is this really the thing that is having the impact that I want? Right? And so we'll just discuss this in the next example. I don't need you guys to actually answer this question. I've decided, I wrote it earlier, but I don't need the answer. We'll just talk about it. So in the example we saw yesterday with the hockey players, right? The results ended up showing that there's not an even distribution of the birthdays throughout the year for people who make it to the NHL, right? We ended up seeing, right, the component here that contributed the most to that the chi-square statistic is the January through March quarter, right? It had the largest variance between observed and expected, and it contributed the most to the chi-square statistic. This gives evidence to what the author of this study claimed. Students hockey players that were born earlier in the year are more likely to make it to the NHL. This data supports that. So we can make a follow-up claim or a follow-up conclusion that's more specific than just saying that the distribution is different. We can then say, based on these results, there's evidence for this other claim that's a little more specific. So that's our follow-up analysis. And we can do that only when we get significant results. Right? Is there anything I can clarify about that? It's like there's literally like a paragraph about it in the textbook, but the fact that they brought it up as an objective, I wanted to make sure that we covered it. All right. So then that concludes the Desmos activity. Let's stop that. Whoa, yeah. Stop sharing my screen. Okay, so I do not quite have the practice problems up in Canvas yet. I should have those probably tomorrow. I'll have those up. And I'll try to have all the rest of the resources for Chapter 11 available by the end of the week. So that if you do want more practices with this particular section, there will be some. Section 11.2 is what we'll get into next week. From what I can tell, 11.2 is a little bit more robust than this first section. So I'm hoping we can get through it in next week, but we will see. We'll see what time allows us to do. If there's any questions, comments, concerns, please tell me. But other than that, have a great rest of your day, and we'll see you all next week, and have a great weekend.